Now we're going to make our functions a little bit more complicated. We're going to look at limits at infinity of rational functions. So here I've got a little fun fact. You could call it a theorem here. It says to find the limits of rational functions at infinity, we look at the limit of the leading terms. And when I say the leading terms, I really mean the leading terms of your numerator and your denominator. So we're actually going to use a really similar trick that we did with polynomials. I'm going to look at the leading term of the numerator and the leading term of the denominator, simplify that as much as I can, and then take my limit. So let's look at a few examples here. So first up, I've got limit as x approaches negative infinity. I've got 4x to the 7th power minus 8x divided by 6x to the 4th plus 9x squared. So the first thing I'm going to do is identify what are those leading terms of the numerator and the denominator. So we're just picking out the term that has the highest power in both the numerator and the denominator. I'm going to need both of them. So in this case, my leading term of my numerator is 4x to the 7th. In the denominator, I've got 6x to the 4th power. So essentially what I'm going to do is ignore everything else except for those two terms. I'm going to rewrite this limit as x approaches negative infinity of 4x to the 7th divided by 6x to the 4th. And now a few things should happen here. If you can simplify your coefficients, in this case 4 over 6, those are both divisible by 2. I can simplify that. I'll divide them both by 2. So limit as x approaches negative infinity, here I'm going to have 2 over 3. The other more important part is we're going to have, hopefully, some powers of x that we can cancel. Here I've got x to the 7th divided by x to the 4th. I can cancel x to the 4th from both of those, and that's going to leave me with x cubed in my numerator. So this is hopefully kind of looking like something that we saw in our polynomial video, where now I can go ahead and I can factor out our coefficient. Here this is 2/3. So I can say that this is 2/3 times limit as x approaches negative infinity. We could say x cubed over 1 if we wanted to, just to keep that x cubed up in our numerator. But I could also, write this as just x cubed here, since x cubed divided by 1 is just x cubed. So I want to right now just look at what is this limit here. What is the limit as x approaches negative infinity of x cubed? If you need to, go ahead and draw yourself a little reference picture of x cubed. I know it looks something like that. We're approaching negative infinity, so I want to move to the left. As I move to the left, my y value is decreasing. It's approaching negative infinity. So here I'm going to have 2/3 times my limit is negative infinity. 2/3, which is a positive number, times negative infinity, which is a negative. Here I'm going to end up with negative infinity for my first answer. So this is a really nice situation that we have here. It's a really nice theorem that we have because it simplifies our problem so much. We get to simplify it just by looking at these two terms to begin with, but then even after that we can simplify our coefficients and our powers of x. Let's look at another example here. Next I've got the limit as x approaches positive infinity, 5x plus 11 divided by 7x cubed minus 2. So again, I want to identify what is the leading term of my numerator, what is the leading term of my denominator. Here in my numerator, it's 5x. In my denominator, 7x cubed. So I get to ignore everything else. I get to say, all right, I just want to look at the limit as x approaches infinity of 5x divided by 7x cubed. So here in this case, 5 over 7, that's not going to simplify, and that's not really a problem. The x over x cubed, though, I can cancel a power of x from both my numerator and my denominator. So this is the limit as x approaches infinity, 5 over 7x squared after I cancel my like powers of x. So, okay, this is a little bit nicer, but I still think that we can simplify this a little bit by factoring out that coefficient. I don't like to deal with coefficients until the very last step. I'll worry about those later. Limits are already tricky enough as it is, so why make it more difficult? So I'm going to factor out that 5 over 7, and that's going to be 5 over 7 times limit as x approaches infinity. Since I don't have anything left over in my numerator, I got to have something, so we'll put a 1 over x squared. So now I'm just going to look at this limit. What is this limit approaching? Now we said earlier, if you have x approaching positive or negative infinity, you have a constant in your numerator, and you have a positive power of x in your denominator. That limit is always, always, always going to be 0. So that limit is going to be 0. That 5/7, that coefficient is going to come down. But I end up with 5/7 times 0. Well, I know if I take anything times 0, I'm going to get back 0. So there is my limit. Let's take a look at one more here. I would encourage you to pause the video right now and try this problem out for yourself. See how we're feeling about it. See if we can at least simplify it to the point where we're going to evaluate the limit. All right, so let's check our answer here. Leading term of our numerator is 10x squared. Leading term of our denominator is negative 5x squared. Be careful and remember that the leading term is not always the first term. It's the term with the highest power of our variable. So I can simplify this. I can look at limit as x approaches infinity. I'll have 10x squared divided by negative 5x squared. Here in this case, okay, 10 divided by negative 5, I can simplify that. That's going to be negative 2. Oops, we'll carry down our limit 2. So we've got negative 2, and then if we look at our powers of x, here we have x squared over x squared. Something really interesting happens here where actually all of our powers of x cancel. We're just left with negative 2. If you want to keep this as a fraction, you could say negative 2 over 1, or we could just say negative 2. But this is the limit I'm left with. I'm looking at the limit as x approaches infinity of negative 2. Here in this case, if I look at what I'm taking the limit of, negative 2 or negative 2 over 1, it doesn't depend on x. There is no x here. There's no power of x. There's nowhere for me to plug in x or anything like that. So it doesn't depend on x. So it actually doesn't matter what x is approaching. It's just always going to be negative 2. It's always going to be, if you want to say negative 2 over 1, or just negative 2. There's our limit. So when we look at these limits at infinity and negative infinity of rational functions, we can end up with a lot of different situations. We can end up with a limit of negative or positive infinity, like we did in our first example. We can end up with a limit of 0, like we did in our second example. Or you can end up with any other finite number. Here in this case, we ended up with negative 2.